Hello everybody and welcome to another problem-solving session. This one is focused on applying Kirchoff's laws to solve circuits problems. Hopefully you've had a chance to either read in the chapter or watch the video on Kirchoff's laws, but broadly there are two rules that you have to follow. One is known as the loop rule. When you proceed around a loop in a circuit, the sum of the voltage gains and drops has to add up to 0 by the time you get back to where you started from. And the second is a junction rule, which says that all the currents coming into a junction have to equal all the currents flowing out of a junction. And we're going to apply those two ideas to solve some problems here. So the first problem says in the figure, the ideal batteries have EMFs of 10 volts and 5 volts. Now, EMF is an odd notation here. It gets that little script E. It has units of volts, but what we use it for in the context of circuits is to cue you in to the fact that you can treat these as ideal batteries. Real batteries, as the chapter details a bit later, have some internal resistance, and therefore the potential difference from one end of a battery to another changes a little bit as you use it in a circuit, and it changes depending on how much resistance is in that circuit. And we don't want that complication in our calculations. So we're always going to treat this like this is a perfect always 10 volt battery and this is a perfect always 5 volt battery. So we want to know how much current there is in resistor 2 and resistor 3. I'm going to start by actually redrawing the circuit because I'd like to add some details to that circuit diagram, and there's not a ton of space in the one that they provide in the figure. I'm also going to go ahead and just plug in the numbers for the resistor and the battery that we have in here. So let's see, this is a 10 volt battery. Over here is a 5 volt battery, and each of these are 4 ohm resistors. All right, so there's our circuit. There's a couple of things you need to do to set up a circuit, and that is to figure out how many possible different currents there might be in this circuit. Well, for example, one current might be pushed through this battery, and whatever current is pushed through the 10 volt battery also has to go through the resistor labeled R1. So I'm going to go ahead and just draw an arrow in the direction that I think that current will go through battery 1, and I'm going to label that I1 since it matches with resistor R1. I'm going to do the same thing for R2. I'm going to guess that the current here is going to go to the left. I'll call that one I2. And then I'm going to guess that they come together and push a current down through resistor 3. And I'm going to go ahead and call that one R3. All right, so a couple of comments about this. First of all, it doesn't matter what direction I assign to those currents. Now, I made an educated guess, and I think I'm probably right about the direction of those currents, but at this stage, it's a completely arbitrary thing. Current can only go one way or the other in a circuit, so you make a guess when you're doing the setup of the circuit, and then it turns out if your answer comes out to be negative, you just guessed the wrong direction, and the current is actually in the opposite direction. Second thing I need to do is figure out how many loops I have in the circuit, and I actually have 3. I could start here and go around this left-hand loop. I could start maybe here and go around the right-hand loop, but I could also start here and go around the perimeter of the whole circuit. So I have up to 3 loop equations that I can generate. Similarly, I also have a junction up here where multiple currents are coming together and a junction down here, so I could generate up to 2 junction equations. Well, I'm going to start with the left-hand part of the circuit. I'm going to call that loop 1, and I'm going to choose to proceed around loop 1 in a clockwise direction. Again, completely arbitrary. I could go the opposite direction just as easily, but this is an arbitrary choice. And you also pick a place to start moving around the circuit. So I'm going to use apply the loop rule and generate a couple of equations here. So to apply the loop rule, I pick a starting place. Let's pick this junction. I've already said I'm going to go around this loop in a clockwise direction. So if I go through this, the first thing I run into is a battery. I pass through the battery from the negative side to the positive side. So that is an increase of 10 volts of potential difference. The next thing I pass through is this 4 ohm resistor. Well, that would be a potential difference across this resistor, and I could write it as a voltage, but it's going to be easier in the long run to use Ohm's law, voltage equals current times resistance, and write this instead as resistance times current. Now, I know what the resistance is. That's 4 ohms. I don't know what the current is, so I'm just going to leave that symbolic as I1 for right now. But it's a drop because I'm going through the resistor with the current. Just like if you're on a river floating on a tube and you are going with the current, you are going to lower and lower elevations, and that's lower and lower energy states. Next thing I would pass through is the 4 ohm resistor here. So that's minus 4 ohms times I3. And then I'm back to where I started, and the loop rule says all those voltage gains and drops have to add up to 0. Okay, I'm going to apply it now. I'm going to go over here and say this thing over here is loop 2. I'm going to also go around it clockwise, but it doesn't matter. And hey, let's start in the same place. Well, the first place we would run into if we go around this clockwise is this resistor in the middle, but I'd be going through the resistor against the current. That's like paddling upstream. So that's a gain in electric potential. So plus 4 ohms times I3. Through this 4 ohm resistor, again, it's a gain plus 4 ohms times I2. Then I run into this battery, but I would pass through this battery from the positive side to the negative side. So that would be a drop of 5 volts. And I would get back to where I started, so that also has to equal 0. Now I could have chosen to go around this loop in the opposite direction. I'd then have a plus 5 and a minus 4 times I2 and a minus 4 times I3. But that's what you get if you just take this equation and multiply everything by -1. So really that's not a different equation. All right, I can also apply the loop rule to the whole perimeter, but it turns out that equation is not unique from the first two. It's basically what you get if you add these two equations together, so I'm not going to bother do that. Instead, to make my next equation, I'm going to apply the junction rule, which says all of the currents coming into a junction plus all the currents going out of a junction must equal 0. So if I look at this junction up here, I1's coming in, I2's coming in, I3's going out. So I'm going to write that as I1 plus I2 minus I3 equals 0. Some people prefer to write I1 plus I2 equals I3, in equals out. You can do that whichever way you want. Algebraically, they're the same. Well, there's 3 things I don't know, I1, I2, and I3, and I've generated 3 equations. Algebra tells me that's enough to solve. By the way, if I chose this junction down here, I wouldn't get a unique equation anyway, because this would just be I3 equals I1 plus I2, or I3 minus I1 minus I2 equals 0. That's the same as the equation I generated here, except for a sign change. All right, so you can proceed in a number of ways here, and this point is algebra. If you know how to do some linear algebra, you can go ahead and put this into a 3x3 matrix. If you are inclined to do things on the internet, you can Google for a 3-equation solver and plug numbers in there. I'm going to do this the old-fashioned way and hopefully not screw it up. I got I1, I2, and I3 here. This one has I1 and I3. This one has I2 and I3. So what I'm going to do is actually solve this first equation for I1. So if I moved I1 over to this right side and then divided by the 4 ohms, I'd get I1 equals to 10 volts minus 4 ohms times I3, all divided by 4 ohms. And that is equal to, let's see, 10 divided by 4 is the same as 5/2, a volt per ohm is an amp. 4/4 is just 1, so 5/2 of an amp minus I3 is what I1 is. I'm going to do a similar thing, take this second equation and isolate I2. So if I do that similar process, I2 is going to equal positive 5 volts. If I move the 5 volts over to the right, let's see, minus 4 ohms times I3, and that whole thing will be divided by 4 ohms. And 5/4 gives me 5/4 of an amp, or 1.25 if you prefer decimals. 4/4 again is 1, so this is minus I3, and this is I2. Now, why did I do that? Well, I now have an expression for I1 and an expression for I2, and I can plug them both into this junction rule equation so that I have an equation that just has I3 in it as the unknown. So let's go ahead and do that. Let's see, I1 is 5/2 of an amp minus I3, that's I1. I2 is 5/4 of an amp minus I3, and then I just have I3 here on its own, equals 0. Okay, let's get all the I3s over on the right-hand side. So that's going to be 3 I3 over here. Here I'm going to have 5/2 of an amp plus 5/4 of an amp. That's going to be what, 15/4 of an amp if you add those two fractions together. 5/2 is the same as 10/4. 10/4 and 5/4 is 15/4. And then if I divide through by 3, I see that I3 is equal to, what is that, 15/12 of an amp. You can reduce that, of course, if you divide both of those by 3, and that's 5/4 of an amp. Or if you prefer, 1.25 amps. But now I have enough information to also figure out what I1 is and I2. And so if I plug that in for I1, I get 5/2 of an amp minus 5/4 of an amp. And that ends up being 5/4 of an amp, or 1.25 amps. Plug I3 in here, I get 5/4 of an amp minus 5/4 of an amp, and I find that I2 is actually 0. And so what this means is in this circuit, this 10-volt battery is pushing a current around this loop. But because this battery is essentially trying to push a current to the right through this 4 ohm resistor, while this battery is trying to push one to the left, they are essentially at a stalemate because of the equal resistance in all the branches, and you get no overall current here. You can also check your reasoning on these Kirchoff rules problems. You can go back in here and say, like, okay, let's see, 10 volts, and then if I1 is 1.25 amps, 1.25 amps through a 4 ohm resistor is going to be a voltage drop of 5 volts. So up 10, down 5, down another 5, and I'm back to where I started. That checks out. Or I2 is 0, right? So up 5 plus 0, there's no voltage difference across here if there's no current flowing. Minus 5, because 4 ohms times 1.25 amps gets me back to 0 where I started from. So these appear to check out with our original circuit. Of course, they're not always going to be 0. So let's look at another problem where indeed they're not. This is a very similar circuit to the one we looked at first. E1 is 6 volts. E2 is 12 volts. R1 is 100 ohms, R2 is 200 ohms, R3 is 300 ohms. They give me a little more room on these, so I may just use their circuit diagram. This is 6 volts. This up here is 200 ohms. This is 300 ohms. This here is 100 ohms, and the battery E2 is 12 volts. All right. So again, I have to designate my unknown currents, and I'm again going to assume the current going through here. Well, since it's through R2, I'm going to call this one I2. The current going through resistor 1, I'm going to call I1. And the current through resistor 3, I am going to call I3. And again, the direction I choose for those is completely arbitrary, but it's an educated guess based on the way the batteries are arranged. And I'm going to just do the same thing I did last time, which is use 2 loops and go around both of them in a clockwise fashion. All right, let's do loop 1 here. I start down here, or here I guess. I go up by 6 volts first, so this is loop rule equations that we're generating here. I go up 6 volts. I then hit resistor R2, so that's a drop of 200 ohms times I2. And then I hit resistor R1, that's a drop of 100 ohms times I1. Back to where I started, equals 0. Over here, if I do the similar thing, I'm going to go plus 100 ohms times I1 plus 300 ohms times I3 minus 12 volts, and I'm back to where I started, so that all adds up to 0. Again, I could go the outer loop here, but that's not going to give me a unique equation that will help me solve for the unknown current. So I have to look at one of the junctions. If we look at the junction at the top, the currents coming in are I2 and I3, so we would have, let's see, minus I1 plus I2 plus I3 equals 0. And there I have my 3 equations that are going to allow me to solve for the unknown currents. Okay, so same thing I did here. I'm looking, I got 2 and 1, 1 and 3, so I'm going to solve this one for 2, this one for 3, plug them both into here to find out what 1 is. So if we can do the algebra, let's see, I2 is going to equal 6 volts minus 100 ohms times I1, all divided by 200 ohms. So here's where I go off the rails because I like fractions and most people don't. This is 3/100ths of a volt per ohm. That's 3/100ths of an amp, or if you prefer, you could write that as 0.03. 100 over 200 is minus 1/2 I1. So there's an expression for I2. Let's take this one down here a bit. I'm again trying to isolate I3. So I3 is going to equal 12 volts minus 100 ohms times I1, all divided by 300 ohms. 12 volts divided by 300 ohms is the same thing as what? 4/100ths, and I'm going to leave the common denominator of 100 because I'm going to need to combine things here shortly. Amp 1 over 3, so that's minus 1/3 of whatever I1 ends up being. And now both of these equations can feed in over to my junction equation, which will allow me to write a single equation that has I1 only in it. Okay, so minus I1 plus whatever I2 is, so that's 3/100ths of an amp minus 1/2 of I1 plus I3, we showed that was 4/100ths of an amp minus 1/3 I1. That all equals 0. Let's see, all my I1 terms are negative, so let's take them over the other side. But the common denominator here is going to be 6, right? Because I got 2, 3, and 1. So this is going to be 6/6 plus 3/6 plus 2/6. So over here I'm going to have 11/6 times I1. Here I've got 3/100ths of an amp plus 4/100ths of an amp. That is 7/100ths of an amp. And the fractions are not getting pretty on us. Let's go ahead and solve for I1. This means that I1 is equal to, let's see, 6 times 7, 42 11 hundredths of an amp, just like you expected right at the beginning. If you prefer, you can write that as a decimal, and that is approximately 0.038 of an amp. All right, now that I know I1, I can plug that in and get I2 and I3. So I2 we had was 3 hundredths of an amp minus, and now we need half of I1. Well, I1 is 42 11 hundredths, so that's 21 11 hundredths of an amp. So if I make that common denominator, this is 33 11 hundredths minus 21 11 hundredths, so that is 12 11 hundredths of an amp. Again, for those of you that are not excited about fractions, that's about 0.11 amps. If I plug in here, let's just keep track of answers, plug in here 4 hundredths of an amp minus, let's see, 1/3 of this. Well, 1/3 of this is going to be 14 11 hundredths of an amp. Again, the common denominator is going to be 11 hundredths, so 4 hundredths is the same as 44 11 hundredths. 44 minus 14 is 30 11 hundredths of an amp, or about 0.027 amps. And it's a good idea to check yourself, because if you're anything like me, you make algebra errors, you make especially sign errors, but these, let's see, 30 11 hundredths plus 12 11 hundredths is indeed 42 11 hundredths, so all of these currents work in terms of the junction rule. So let's go back and just make sure we've answered what the question says. What is the size and direction of the current through resistor R1? Well, here's resistor R1. That's I1, and we found that to be 42 11 hundredths of an amp. And because our answer came out positive with our initial guess of down, that tells us that down is the correct guess, and it is indeed in the downward direction. R2. I2 is going through R2. We found it to be 30 11 hundredths of, whoops, I'm on the wrong one. I2 is here. 12 11 hundredths of an amp. And again, we guessed right. It came out positive, so it must be positive. The current through 3 must be to the left, because we guessed that and our answer came out positive. That was 30 11 hundredths, or about 0.027 amps. There's one other piece that we have to answer here. What is the electric potential at point A? And that's the reason for this little symbol that is shown here in the circuit diagram. That little symbol tells us that's ground. Assume right here is a voltage of 0. So if this is a voltage of 0, and I put my voltage meter on here, what would I measure if I left one lead here and put one lead up at point A? Well, there's a couple of ways you can approach this, but the easiest, in my opinion, well, you can pick any path you want to add up the voltages. Well, let's pick the path through the middle of the circuit, because if I started at 0, the only thing I would do is add the voltage difference across the 100 ohm resistor, and I'd be at whatever the voltage at A is. So this is part G. The voltage at A is equal to the current I1, so we figured that was 42 11 hundredths of an amp, times the resistor of 1, that's 100 ohms. So this ends up being what? 1100, 42 elevenths of a volt. The last piece we're looking at, number 3 on this problem set, is used to illustrate that, things can get pretty hairy pretty quick, because in the circuit that the two circuits that we just looked at, there were three. So I have 1, 2, 3, 4, 5 resistors in here, which means I have at least 5 different currents that are in this circuit. Now, whatever goes through this resistor is also going to go through this battery, so that's not any different. But there would be a current going through this battery, presumably, unless it was some reason 0, which means this is a circuit that has 6 different values of electric current, which is a heck of a lot, and you would have to write 6 equations with 6 unknowns and proceed from there. And that's an incredible amount of work. It's not as challenging because all the resistors are the same, but you know, who wants to do all of that algebra? That would be somewhat nightmarish. Well, it turns out that you can simplify your work by the realization that whatever current comes into this resistor, let's say it's going up, I don't know that it is, comes here and has to split between this resistor and this resistor, but then comes back together to pass through the resistor where we want to know what the current is, where I2 is. And so it's possible to treat all of these resistors as just a single resistor. And we're going to learn about that next when we learn about series and parallel resistors in circuits. So a piece of which I'm going to do right here is not going to make any sense to you unless you've done series and parallel circuits before. Knight is a little bit odd in that he does Kirchoff's rules before series and parallel, and most other books do the flip. But I'm going to use this to illustrate that, number one, some Kirchoff problems can get super challenging, but number two, if you have other analysis techniques that you can use to simplify the problem, by all means, you should still try to do so. So each of these are 5 ohm resistors. And it turns out that 2 5 ohm resistors wired in parallel like they are here are equivalent to 2.5 ohms of resistance. And then I have another 5 ohms of resistance and another 5 ohms of resistance. So collectively, this whole network has 12.5 ohms of resistance. So again, if you're not familiar with that concept, just put a pin in this and you can come back and look at it after you've dealt with series and parallel resistors. But I just wanted to show you that if you take my word for it, I can draw an equivalent circuit, meaning it would behave the same electrically as the original circuit, but it's going to be much, much easier to analyze. So here's 12 volts, here is 5 ohms of resistance, here is 5 ohms of resistance, and here is 4 volts. And now that I've done that, this is actually easier to analyze than either of the 2 problems we looked at previously, because if I apply my Kirchoff thinking, I realize right here I have a loop, and so I have to be able to add voltages in that loop. This is I1 right here, whatever I1 happens to be. Let's guess that it's going down. If that's the case, the loop equation would look like plus 12 volts going through this, and then minus 5 ohms times I1 equals 0. Look at that, only one unknown. So I1 is going to equal 12/5 of an amp, or 2.4 amps. I didn't even have to do algebra of combining multiple equations. Now, if I know that, then I can sum either around this loop, or I can sum around the whole outside, and I think I'm going to go ahead and do that. So let's go ahead and sum around the outside. Let's just guess that I2 is going down in this resistor over here. Whoops, I need to say that this is 12.5 ohms because it's taking the place of all of my resistor network. Okay, so if I go around the whole outside perimeter and write another loop equation, I'd have plus 12 volts minus 12.5 ohms times I2 plus 4 volts equals 0. Again, one equation, one unknown, I can solve for I2 pretty directly. I2 is going to equal 16 volts divided by 12.5 ohms. So fractionally, that would be what, 32/25 of an amp, or if you prefer, 1.28 amps. And notice we did this without having to put a whole bunch of equations together. So this is the end of the example problems for problem solving for Kirchoff's laws. As always, if you find an error in my solutions, I appreciate you letting me know about that. Thanks.